Hi everybody, it's Dr. Chabot, and in this video we're going to solve a problem using Coulombs law. And in this course I have what I call the physics toolbox. And within this toolbox it's the summary of all the main concepts, but it also has these very specific problem solving steps along the way for some of the types of problems that we're going to encounter. This is the first of those steps, and this is for solving problems with Coulombs law. And so I encourage you to use that as a reference in addition to the example that we're going to work through. You'll see that as I work through it, I will be following very specific setups that you can follow in any problem of this sort. All right, so let's go and see what our example is going to be. This is our example. I have 3-point charges in this space. I have Q1, which has a charge minus 4Q. And then a height h above that, I have Q2, which has a charge plus 3Q. And then I have a charge Q3 that has a charge minus 2Q. It's a distance, horizontal distance d away from Q1. Now, in this problem, you aren't yet told, right, what you're looking for. You have to actually kind of tunnel vision in a problem on one of the charges. And so in this one, I would have to say, for example, find the net electric force on Q3 due to Q1 and Q2. That means that we're going to tunnel vision looking only at what is happening to Q3 and find that net force. So that's going to allow us to have a solvable problem. Each charge, of course, experiences a net force, and that's the phrasing of the problem is what lets you know which one that you're focusing on. So the first step is always to draw a figure. A figure is essential in so many different physics areas. And in the figure that you're already provided, we also want to add some details. So one thing that was missing is this distance between Q2 and Q3. So just using our properties of the right triangle, we see that that's h squared plus d squared. The other thing that's missing, and is sometimes useful, is we want to pick an angle to define. And it doesn't matter which angle you define here in your triangle, but you will want to do that because fundamentally we're adding force vectors. And if we're adding vectors, we're going to need components. So we're going to need an angle to talk about. And so we're going to just now use that as our first sketch. So that's step one was our sketch. Now step two is going to be to draw. So this was step one. Step two is going to be to draw essentially the free body diagram. So we're going to draw the free body diagram that shows the net, shows the forces, the individual forces, not just the net force, shows the individual forces on Q3, because those are the vectors that we're going to be adding. So I'm going to draw Q3 here, and it's going to have two forces acting on it, one from each charge. It's a negative charge itself, so it's going to be repelled from Q1. So I'm going to have here, I'll label this the force that Q1 exerts on 3. Don't worry about making your subscripts long if it helps you understand what's happening. And so that one's going to point directly away because it's a repelling force. I'm then going to have an attractive force between Q2 and Q3 because Q2 is positive and Q3 is negative. So I'm going to then have a force that points towards Q2 from Q3, and that's going to be a force that 2 exerts on 3. And those are the two vectors that I need to add. So that's the simple next step, is to visualize your vectors. You always need to visualize your vectors. If you are adding vectors without visualizing them, you are doing it wrong. All right, so then what we have here is we then can go on to step 3, which is simply going to be to find the magnitudes of the vectors. So get the magnitudes of each vector. And that's going to be from Coulombs law. So the Coulombs law is that the force between two charges, 1 and 2, is equal to K, and this is all magnitudes, Q1, Q2, over the distance between them squared. So the absolute value signs are here. We're not putting in positive and negatives. We're just taking a magnitude. And so the magnitudes of each vector here, the magnitude of the force 2 on 3, and I'll keep my color coding going. So the magnitude of the force that 2 exerts on 3 is simply going to be equal to K times Q2 times Q3. So I'm going to put here, again, it's magnitude, so I'm going to say absolute value of 3Q times the absolute value of minus 2Q. So that negative's going to go away, all over the distance between them squared. So I'm going to get the square root of h squared plus d squared squared. And so when I then work this out, I can see that I end up with a 6K capital Q squared all over, and then this bottom is just h squared plus d squared. And again, I took the absolute value, that's just a magnitude at this point. That is literally the length of the vector, right? The magnitudes are the length of that vector. For the force that 1 exerts on 3, so 1 on 3, we do a similar thing and we end up with the magnitude of K, and then it would be the absolute value of minus 4Q times the absolute value of minus 2Q, all over the distance between them squared, which is d squared. And so then that one becomes K, and then, 8, I'll put the 8 first. So 8 K, Q, capital Q squared, all over d squared. And that, again, is the length of that other vector. Good. So we are just doing vector addition. And so the next thing that we need to do after we find magnitudes of vectors is we need to add them to their components. We need to find their components, right? So we need to find the x and y components. You cannot add vectors any other way. There are no shortcuts. And so depending on how you like to write out the components, sometimes people like to make a table in order to visualize these and kind of keep your work organized. So we have here the x and the y, and then we have the force that 2 exerts on 3. And this is where our original diagram comes in handy in order to visualize the vectors. And remember, when you're doing components, you say, is it plus or minus, and is it sine or cosine? So in this case, for my x component, we can see that it's in the negative direction. So it's going to be the negative of the magnitude of F2 on 3, which we already found above, and then times, and if we look to see where this angle is, that angle theta is that same angle theta here, so it's going to be times the cosine of theta. The y component is upward, so it's going to be positive times the magnitude of 2 on 3, and then it's going to use the sine of the angle. So remember, that's just because the sine is the opposite over hypotenuse, the cosine is adjacent over hypotenuse. So that's why I chose the sine and cosine as I did. So for this other vector, the force that 1 exerts on 3, we see that it's only actually in the x direction. So the x component is positive times the magnitude of the force that 1 exerts on 3. And there's no sine or cosine because it's just in the x direction. The y component is simply 0. So now we are ready to talk about the sine and cosine because the theta wasn't in the problem. So step 5 is to put sine and cosine in terms of the sides of the triangle. And so this is just using our SOHCAHTOA, right? So this is just going to be using SOHCAHTOA. And if we look at our original figure, we can see that the sine of theta is going to be the opposite, h, over the hypotenuse. And so we can say here that sine of theta is going to be equal to h over square root of h squared plus d squared. And we would see similarly that cosine of theta is adjacent, which was d, over the hypotenuse, h squared plus d squared. So we can use these then for our sines and cosines in our equation, since we weren't given theta in the problem. And so then now we are simply ready to do our next step, which is to add the components. So you add your components. And in order to do this, we just then get the net force on 3 in the x direction is going to be equal to, and we simply add up our x components here. So we end up with negative, and I'm going to plug in for that magnitude, so negative times 6k capital Q squared over h squared plus d squared, and then times the cosine of theta, which is, remember, d over square root of h squared plus d squared. And then I'm going to add that to the magnitude of the force that 1 exerts on 3. So 8k capital Q squared over d squared. This doesn't really simplify very much. That is just what our x component looks like. The only main simplification I can make is that these the denominators of this first fraction could be written as minus 6k Q squared and then times d all over, and then this is h squared plus d squared to the 3/2 power. So that's one simplification we can make, plus 8k capital Q squared over d squared. So that's going to be my x component. So that's my x force in the x direction. And then similarly, I'm going to have my force in the y direction doing this same sort of thing. So the force in the y direction, though, I only have that one component of the vector. So it's going to be simply positive the force that 2 exerts on 3, that magnitude. So that's going to give me a 6k Q squared over r squared, but times the sine theta is going to give me a factor of h on top, and then on the bottom, h squared plus d squared all to the 3/2, kind of jumping straight to that simplification. And so that is my net force. There isn't another step, because if it just asks you for the net force, then component form is perfectly valid. However, if it did ask you for a magnitude and an angle, remember, and step 7 is simply to recall that you can get the total magnitude of the net force by simply taking the square root of fx squared plus fy squared, and that you can get the angle it makes by doing the inverse tangent of f sub y over f sub x. So that's just some recall of basic vector addition and properties. So in this problem, unnecessary, since unit vector notation is perfectly okay. All right, so I hope that this helped clarify, and remember that we do have these toolbox steps that you can follow along with at any time, and you'll find those in your course packet.